One of the biggest improvements in power delivery in the past few decades was the process of transitioning from large, bulky iron core transformers and linear regulators to small, slick, and quite often noisy switching converters. Although using switch mode power supplies greatly improves the efficiency when compared to a linear regulator, and the overall size when compared to a mains transformer, these sort of converters aren't without fault. So hello and welcome back. Today I will start looking at what are some of the most common techniques that can be used to reduce the electrical noise of a switching converter. However, before reducing the noise, we need to first understand what exactly makes the circuit noisy in the first place. Where exactly is all the noise coming from and why? So if you're curious, then keep watching. To start things off, it's important to understand that electrical noise will exit the power supply in multiple ways. You have your conducted noise, whatever exits through the input and output wires, and radiated noise, whatever exits in the form of a field. In the short range or near field, this will take the form of electric and magnetic fields, and in the far field, the two combine into a single electromagnetic field. Both of these can and will be problematic in the real world. Now, to get a better grasp of how all the noise is being generated, it's easiest to first separate it into voltages and currents. So let's now actually start with a basic voltage and current analysis. So how do the typical waveforms look within the converter? This can be done in a circuit simulator, but also with a bit of paper. As an example, if we look at a boost converter, we have three voltage nodes: the input, the output, and the switching node. And only the switching node is switching. So here, typically, we will see a square wave. Now, this is the main voltage noise source node of a converter, and the spectrum of this will contain a fundamental at the switching frequency and a set of upper harmonics. The exact amplitude of the noise will of course be dependent on the amplitude of the voltage transition. The larger the voltage swing, the larger the noise, and the exact distribution of harmonics will also depend on the duty cycle. Now, if you actually measure the switching node of a running converter and zoom in a bit, you will observe that it's not really a perfect square wave. There are quite a lot of things going on here, but the first thing to highlight is the exact transition from one value to another. It's not instantaneous. So the first approximation is that it's a trapezoid wave with a clear rise and fall time. The switches never transition instantly, so it does make sense to have a certain amount of time for the transition to occur. Now, if we simulate such a waveform, so for this I prepared two pulse sources, and if we just have a look at these are trapezoid waveforms with different rise and fall times. So one of them has a 0.01 microsecond rise and fall time, and the other one has a 0.1 microsecond fall time. And well, we look at these in the frequency domain, so by analyzing them with an FFT viewer. So as mentioned before, we see a series of spikes appearing at our fundamental switching frequency and then at upper harmonics. But if we focus on the envelope of the two graphs, we will see two distinct regions appearing. So a range in which the amplitude is dropping at a constant rate of about 20 decibels per decade, and then another range in which the amplitude drops at about 40 decibels per decade. The interface between these two regions is transition time dependent, and it appears at 1 divided by pi times the transition time. For the sake of simplicity, we can consider the rise and fall time to be equal and rename this the transition time. So the exact spectrum shape will be impacted by how fast the switching node transitions between the high and low state. With slower transition times, the interface moves lower. With faster transition times, it moves higher. Coming now back to the real circuit, when your measurement equipment has sufficient bandwidth, and while the converter design is bad enough, another interesting phenomenon becomes visible. Other than the square wave, which is not really square, you also have some high frequency oscillations appearing, at a frequency that's unrelated to the main switching one. Now, these oscillations can be more or less severe, but they will be problematic nevertheless. Now, if we simulate a complete boost circuit using ideal components, and we look into the switching node, and we'll zoom in a bit, we get our ideal trapezoid wave. This is all the noise we get with ideal components. So to be able to reproduce our measurement, we need to start considering various parasitics. To begin with, I only added in a bit of inductance for the two active components and a bit of capacitance because of the various traces. So if we look at the switching node with this sort of circuit, we are starting to see a different story. So on the rising edge, we're getting a bit of a overshoot with a relatively weak oscillation. And on the falling edge, we are seeing a far more severe oscillation. So this is how we get our ringing to appear. And well, if we want to analyze the spectrum of this, so again using the FFT analysis, on top of the noise spectrum of the signal that we previously had, so the one in green, by adding the extra parasitics and thus the ringing, in the spectrum, we are seeing some noise peaks appearing, which are not really derived from the switching frequency. But these will be larger the more high frequency energy there is. So these could be reduced if you increase the transition times, although some better methods do exist. Finally, the last important non-ideal behavior to look at occurs when the converter is running in discontinuous conduction mode. So, as long as the inductor current is always non-zero, and we have a continuous current variation, we call this continuous conduction mode. But when the inductor current hits and stays at zero during the switching cycle, we call this discontinuous conduction mode. Here, the theoretical switching node waveform is still a square wave with an extra plateau appearing, but the real one is, well, this thing. Once the diode no longer conducts, the inductor with the various stray capacitances forms an oscillator. And well, it oscillates until the next switching cycle starts. This is usually oscillating at a higher frequency than the converter, but lower than the ringing we previously observed. Therefore, it can still be quite problematic. So we can also have a look at this behavior. Again, looking into the switching node, if we play around with the load a bit, we can see that these oscillations will appear and disappear. So at small loads, we can see the converter running in discontinuous conduction mode, the oscillation is present in the switching node, and then if you increase the load, this oscillation will disappear. So now, if we analyze in the simulator a converter running in discontinuous conduction mode, so for this I decrease the load, increase the resistance value, so that the current through the inductor can drop to zero. And well, if we look at the voltage in the switching node with the ideal circuit, we do see the expected behavior. So we have our square wave with our plateau voltage. Now, if we just add in the parasitic capacitance in the switching node, and we look at this waveform, now we get our oscillation appearing. So this capacitance, in practice, will be from the layout, but also from the various component capacitances. Finally, if we add in all of the parasitics, so we also include the various series inductances that will appear, then we get all three effects. So other than our oscillation, we also get our ringing that we've previously seen. So now, when we look at the FFT spectrum of these waveforms, so starting from the reference in green, when we add in the oscillation, we get a peak appearing at around 15 MHz, and then when we also add in the other parasitics, then we get an extra peak appearing from the ringing at much higher frequency. So in reality, you can have both of these at the same time. So far, we strictly focused on the switching node, which is supposed to switch and be noisy, to some extent at least. The large amplitude variations of the switching node will also be observed in the near field using electrical field probes. It's not something you want to see, but it will be there unless some special measures are taken to reduce it. Leaving this aside for a moment, if you look closely, you will find noise in other parts of the circuit as well, like the input and the output. The noise is much smaller, we are talking millivolts here, but this is a bit more problematic since this noise is conducted by our conductors to all the other circuits to which the converter is connected to. To better understand the source of this, let's turn to a current analysis first. Now, when analyzing the current in a switching converter, it's usually drawn as it flows in loops. When the switch is on, current flows from the input capacitor through the inductor and then down to ground, and then when the switch is open, the current closes through the diode and into the output capacitor. But for our noise analysis, it's best to look at current as it is flowing through the individual branches. Let's consider a converter running in continuous conduction mode. And to keep things simple, we can also consider the input and output current as constants. But the other currents inside of our circuit are a bit more complex. So with the input capacitor and inductor, we have a triangular current, and with the switch, diode, and output capacitor, we have a pulsating trapezoid thing. Now, from a noise analysis point of view, there are a few major observations to make here. First, the triangular current amplitude is smaller than the other two, so the noise from it will be smaller to begin with. But the other observation is the exact shape. One is a triangle, the other is a sort of trapezoid. So the exact spectrum distribution will also be different. We can have a better look at this in the simulator. So for this, I just kept the reference circuit with ideal components. So if we look here at our inductor current, diode and switch current, and well, we rearrange them a bit, so we can see that our inductor current in green nicely decomposes into the diode current in blue and the switch current in red. And well, if we analyze the spectrum of these three, we can see that all of them have the same fundamental, and while the switch spectrum and the diode spectrum are more or less the same, so we have our two distinct regions, the first 20 decibel per decade drop and then the 40 decibel per decade drop. However, with our inductor, which has the triangular current, first of all, the fundamental amplitude is smaller, but then, since the rise and fall time are the same, and the sum of them equals the period, we only see our 40 decibel per decade drop. So, from a noise point of view, the components passed by the pulsating current are far more critical than the ones passed by a triangular current. Hence, we get this extra loop sometimes, which is called the hot loop. Now, while observing the current in each branch of the power supply is a more challenging measurement, what is a bit more easy to do is to measure the current-generated noise in the form of a magnetic field noise, which is present around the various converter branches. So with this design, when my magnetic probe is close to the triangular currents in the input and inductor, we are getting a certain amount of noise. However, if we look over the switching components, the noise increases dramatically. To finish our initial noise analysis, the last thing that I want to look at today is the input and the output capacitors. As we've already seen, both the input and the output do contain quite a bit of noise, so let's see why that actually is. Based on the current analysis, we know our capacitors are experiencing variable current, so the voltage at their terminals will also be variable. For the boost, the input sees a triangular current, and the output a trapezoid current. So let's see how the voltage on a capacitor looks like when exposed to such a waveform. To highlight this, first I constructed a circuit that applies a triangular current to a capacitor. So this is the current that my sources are providing, and if we look at the voltage present on an ideal capacitor, we see that it's more or less a sine wave, with the sine wave's frequency equal to that of the triangle wave. Now, from a spectral point of view, this is great news, since an ideal sine wave would only consist of a single frequency. Now, things will get a bit more complex when we turn to our trapezoid current. So with the second setup, this is the current that I'm applying, and if we look at the voltage present on the capacitor, well, it looks more or less like a triangle wave. So this is not a perfect triangle, but it's not a sine wave either. So already we can safely say that the voltage noise on the output of a boost converter, where we have a trapezoid current, will be richer in harmonics than the capacitor present on the input, where we have a triangular current. In reality, you will not really see these exact specific shapes, but something a bit more complex. And one of the key problems appears from the real capacitor's equivalent series resistance. No capacitor is ideal, and other than the voltage amplitude caused by the limited amount of capacitance, the other important factor determining the exact noise will be the voltage drop occurring on the ESR. So if we take the previously created circuits and add in a bit of ESR, so I kept the same capacitor, same signal sources, but added in 100 milliohms of ESR, and we rerun and recheck. So with our triangular current, we are getting this voltage waveform, which is no longer a triangle, and with our trapezoid current, we are getting this thing. Now, while the trapezoid current is still more problematic than the triangular one, the key insight here is that the more ESR the capacitor has, the larger the noise amplitude becomes, and more complex in its spectral content. And since the ESR will never be zero in a real component, this is quite an important topic to keep in mind. So finally, we can just check the spectral content of both of these waveforms, and see that other than the fundamental, they also contain a bunch of harmonics, and the one corresponding to our trapezoid current has larger harmonics than the one corresponding to the triangular current. So even if the ideal capacitor has some nice looking voltage waveforms, the addition of the ESR ruins this and makes a far more noisy looking waveform both on the input and the output. Now, if the noise measurement on the input and output is done with sufficient bandwidth, you will also see that other than the non-ideal waveform we looked at previously, we also have some spikes appearing. Now, while usual noise measurements are carried out with a 20 MHz bandwidth limit to measure the exact ripple, if you want to see this high frequency noise, I do suggest to leave your measurement device with higher value bandwidths. So the parasitic element that is missing from our analysis is the parasitic capacitance of the inductor and the diode. It's usually just a few picofarads in the inductor, but the diode can have quite a lot. And this will also be coupled with some other non-ideal effects. Anyway, the result of this is that the high frequency part of the noise, present in the sharp transitions of the switching node, has a way of directly exiting the converter. Now, normally the capacitor would filter this, to some extent at least, but it doesn't do that completely. Some of the noise still makes it through. Again, our ESR is a problem, but an even bigger problem is the capacitor itself. Based on the equivalent model of a capacitor, other than the capacitance and the resistance, we also have some inductance. In other words, the impedance of this series assembly, especially at high enough frequency, will start to increase. The component will no longer behave like a capacitor, but rather like an inductor. So the higher the frequency, the higher its impedance and thus the lower its attenuation characteristics will become. Finally, we can confirm all of our observations in a complete circuit. So you can do this on a practical board, but usually it's best to try things out first in the circuit simulator. So for today, I will be using a modified version of the LT1082 test fixture. Now, while most behaviors will be easy to reproduce, you might find that the more simple a model is, the more things are missing. So it's common to only use capacitance for a capacitor and simply skip over ESR and ESL, and in a similar fashion with inductors, it's very easy to skip over the various resistances and parallel capacitances. Final thing to mention is with the input side, if you want to more accurately reproduce the input capacitor's behavior, it's important to provide some sort of isolation in the input supply. So give it some sort of series resistance and maybe even a bit of series inductance. Then you will get a more accurate representation of what the capacitor does. So if we run the simulation, we can see our high frequency noise appearing in the output, a far more nice looking waveform in the input. We can observe the almost square wave in the switching node with a bit of overshoot. And well, if we start adding in all sorts of inductances, then we can also reproduce ringing and other phenomenon. Now, to get the best simulation accuracy, you will need highly accurate simulation models. Usually, there's nothing wrong with the simulator, but rather with the models that are used. More complex models will provide better results, but also the simulation time will take far longer. In the end, while the analysis that I performed today was strictly focused on the boost converter, a similar approach can be taken for any other topology. By starting off with an ideal model and a practical converter, and after a few measurements, you can slowly add in the various non-ideal elements to recreate the real observed phenomenon in the simulator. Once all of the noise mechanisms are identified, the difficult process of reducing them can begin. Next time, I will be going into a bit more detail with the various components to see how the exact component can impact the amount of noise a given converter generates. But until then, I hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.